Hello everyone, I'm Guanghui from Nanjing University. The title of our paper is DIFER, Differential Automated Feature Engineering. The first is the introduction. AutoFE employs a search strategy instead of human experts to search in the feature space and construct high-quality features from raw data, thus improving data quality and enhancing the performance of machine learning models. The core part, feature construction, is formalized as applying transformations, for example, as arithmetic operators to the raw data. Motivated by the success of NAS, we consider exploring an effective and efficient AutoFE method. However, there exists the following challenges. First, commonly used sequence representation of constructed features has side effects. More flexible and expressive representations are needed. Second, the cause of inefficiency for the existing AutoFE approaches is the fact that AutoFE is treated as an optimization problem over a discrete space. Huge computational costs are needed during the automated search process. Thus, we propose a feature evolution framework to search for better features iteratively. To represent constructed features, we design the path tree structure, which is more flexible and expressive than the commonly used sequence representation. We introduce a novel feature optimizer based on the encoder predictor decoder for feature evolution and thus can achieve differentiable AutoFE. To our best knowledge, DIFER is the first differentiable AutoFE method. Extensive experimental results on a variety of tasks demonstrate that DIFER outperforms the sought-out AutoFE approaches in terms of both model performance and computational efficiency. Next, we introduce the proposed method. We use D to represent the raw data, where F is the set of original features. Through the specified transformations T, we can express the constructed feature space through closures. Therefore, the goal of AutoFE is to find the feature set F star in the feature space that maximizes the benefit of the machine learning model. As shown in the figure, we propose an evolutionary framework to achieve AutoFE. Overall, DIFER is divided into three phases. First is the population initialization phase. DIFER randomly sample and evaluate features from the feature space to construct the initial feature population. Second is the feature evolution phase. DIFER iteratively construct new features by performing gradient-based optimization based on the feature optimizer and exploring the feature space. Feature selection is the final phase. DIFER adaptively selects the top individuals from the population to form F star. As shown in figure, we design a tree-like structure called path tree to represent constructed features. Through the above being F syntax parsers, the original feature in form of abstract expressions are parsed into path trees, and then the corresponding strings is derived through post-old traversal. The feature optimizer is the core of DIFER. It consists of three parts. The encoder is an LSTM, which maps the variable length transverse string to a continuous embedding. The predictor is a 5-layer fully connected MLP, which predicts the feature score according to its continuous embedding. The decoder is an LSTM with the attention mechanism, which maps the embedding to the corresponding transversal string. After jointly training the feature optimizer for convergence, it is used to optimize the constructed feature. Instead of searching in the discrete feature space, the encoder maps the transversal string of the path tree into a continuous space. Thus, constructing a better feature is equivalent to generating better embedding in the continuous space. The following predictor takes the feature embedding as input, predicts its performance score, and directly optimizes the embedding by gradient ascent along the score direction. The optimized embedding is further decoded as a better feature in the discrete space. Next, we show the experimental results. In this part, we use 25 public datasets covering classification and regression tasks and conduct experiments in the above environment. We compare DIFER with the existing AutoFE methods on the above matrix. First, we demonstrate the effectiveness of DIFER. The table shows that DIFER outperforms the existing and sought-out AutoFE methods in all but 4 cases. Same as the differentiable AutoFE method, we show the efficiency of DIFER. In the table, DIFER achieves better performance than the sought-out AutoFE method NFS by using 40 times fewer feature evaluations, while still achieving significant performance improvement. The advantage of DIFER is more significant with the restricted number of feature evaluations. DIFER achieves an average performance improvement of 6.89%, doubling that in table. Moreover, the efficiency advantage of DIFER is more obvious on large datasets that requires more evaluation time. For example, compared with NFS, DIFER can achieve such speed up on these datasets respectively. Moreover, we conducted 2 experiments to evaluate DIFER's ability of exploring the high-order feature space. The left figure shows the number of each order features generated by DIFER. High-order features take a considerable average proportion of 80.9%, confirming that DIFER explores the entire feature space instead of its subspace. In the right figure, the overall performance of DIFER stably increases with the max order k. For most datasets, sufficient performance improvement can be already achieved with the max order of 2. There is no need to set an excessive large max order in practice. Finally, we investigate the generalization ability of DIFER. The results in the table show that DIFER achieves significant improvement on the different algorithms. In this work, we propose the first differentiable AutoFE method DIFER. DIFER leverages an encoder-predict-decoder-based feature optimizer, which maps features into the continuous space, while the encoder optimizes the embedding along the gradient direction induced by the predictor and recovers better features from the optimized embedding by the decoder. Based on the feature optimizer, we propose a feature evaluation framework to search for better features iteratively. Experimental results show that DIFER is effective on both classification and regression tasks and can outperform the existing AutoFE methods in terms of both prediction performance and computational efficiency. For feature work, we plan to automatically search for transformations for different feature types. Thank you for your listening.